Okay. Today we shall discuss about the separability of the non-commutative space coordinate degrees of freedom with the generalized Peres-Horodecki separability criteria, which is actually introduced by Simon and Simon's criteria for a bipartite Gaussian state. And we know that, and we will focus our discussion in non-commutative space, since we know that the transformation between the usual commutative space and non-commutative space is non-symplectic. So the immediate application of Simon's separability criteria for non-commutative space is not straightforward. So it's transformed the non-commutative space system to an equivalent Hamiltonian in commutative space through Bopp shift, which enables us to utilization of the separability criteria in NC space. The system is transformed into canonical form, keeping the intrinsic symplectic structure, which is SP4R group, intact. It turns out that the existence of the NC parameters in the oscillator determines the separability of the states. In particular, for isotropic oscillators, the separability condition for the bipartite Gaussian states depends on NC parameters. Moreover, anisotropic parameter values for the oscillator affects the separability. In other words, both the deformation parameter and parameter values of the oscillator are important for the separability of bipartite states. Thus, tuning the parameter values, one can destroy or recreate the separability of states. For practical implication, we illustrate the issue of extractable work from quantum heat engine in non-commutative space for entangled state. First of all, notations. Bipartite pure state of two parties, Alice and Bob, A and B, is entangled if it cannot be expressed in the product form, like phi A tensor product phi B. If it cannot be written like this, we will tell that the state is entangled. And the mixed state can be separable whenever it can be expressed in terms of this. Here, the notation rho AB is the density matrix on the product space. HA is the Hilbert space corresponding to first party A, and HB is Hilbert space corresponding to the second party B. And for the density matrix rho AB for mixed state P, and this is the weight factor. This is the for first party, and this was second party, the tensor product. The partial transposition with respect to the party B reads like this. First party is remains fixed, and the partial transposition operator acting on the second party. So this KL will be transpose LK, and this is a dummy index, so we can change it. So PLK, KL. So this is the partial transposition operation, which will be very vital in our coming discussion. And so we have to remember that the partial transposition operation, in general, transposition operation preserves the eigenvalue. So the non-negative eigenvalues for density matrix will be preserved for transposition after transposition, but for partial transposition, this is not guaranteed. For partial transposition, real non-negative eigenvalues may not be transformed into real non-negative eigenvalues. So we have to check this. And the Wigner distribution, the quasi-probability distribution for the phase space representation of quantum mechanics is defined by the expectation value of the density matrix like this, and Fourier transformation of this. And if we operate the partial transposition operation on the Wigner distribution, one can show that this is the partial transposition on the second party. So P2 will transform as minus P2, and coordinate will remain invariant. And since it's acting on the party B, so the first party operator will remain fixed, and for second party, the P2 will change to minus P2. So partial transposition operator for continuous variable system, something like time reversal symmetry operation. And the coordinate vector, because the coordinate vector, if we define the coordinate vector like this is x1 p1 pair like the first two coordinate, and the x2 p2 pair for the second party, x3 x4, And we can see that the partial transformation transform the coordinate vector like this, where the operator is diagonal 1, 1, 1, minus 1, because P2 goes to minus P2. So for a bona fide density matrix, our requirement is that under partial transposition operation, the separable density operator will transform into a non-negative operator, that is a bona fide density matrix, because for density matrix, the eigenvalues should be non-negative. So the separable density operator will be transformed into non-negative operator. This is our requirement. And this is very strong result proposed by Simon long back. And if we recall the fundamental commutation relation, this is x alpha, x beta. This can be cast into this form, IH cross J alpha beta, where this J is diagonal of J2, J2. This is J2 is 0, 1, minus 1, 0, symplectic matrix. It can be expressed like this: I sigma y. Sigma y is Pauli sigma y matrix, 0 minus I 0. One can quickly check that recall that x1 was small x1, x2 was small p1, so x1 p1 equal to IH cross, and something like this. And the covariance matrix can be defined like this: the expectation value of anti-commutator of x alpha x beta minus expectation value x alpha x beta. These expectation values are evaluated with respect to the Wigner distribution. So, and one can see that with this the covariance matrix element, if we arrange the covariance matrix element into a 4 cross 4 matrix, we can see that this can be written in terms of block matrix V11, V12, V12 transpose, V22. So symmetric matrix. So that's all we will need today. And in terms of this covariance matrix, we can state the uncertainty principle, that is the covariance matrix plus I by 2 H cross J. This is J is this diagonal J2, J2. This should be a positive definite matrix. That means the eigenvalues of this will be positive. So in this equation 8, all the necessary conditions are encoded. This is fundamental requirement for quantum theory. And generic local transformation, this is S12 for two party, S1 plus S2 acts on this covariance matrix like this. This is VJJ, this is the diagonal part. This is SJ, VJJ, SJ transpose. This is, for example, for party A, V11 will transform like S1, V11, S1 transpose, whereas V11 is the first block of the covariance matrix corresponding to party A, and V22 corresponding to party B similarly, and V12, this is the coupling portion which encodes the information of both party A and B. So party for party 1 this is S1, and for Bob this is S2. So V12 will transform like S1, V12, S2 transpose, with Sj is 2 by 2 symplectic matrix over R. So this is a generic local transformation, because for entanglement study, party will perform their experiment locally on their system. So under this transformation, the local invariant with respect to this local transformation is obviously the determinants, and the total determinant of the covariance matrix, and this particular combination trace of V11 J2, V12 J2, V22 J2, V12 transpose J2, where Vij are the blocks of the covariance matrix, and J2 is the symplectic matrix 0, 1, minus 1, 0. So from this well-known result of Williamson, this Williamson's theorem state that any covariance matrix, as the symmetric matrix, can be transformed with the symplectic transformation like this. So V can be transformed into W11, U12, U12 transpose W22, where W11 and W22 are diagonal and with their symplectic eigenvalues. For instance, W11 is diagonal of the diagonal element of W11 is square root of delta of J. This is delta of J is the determinant of the VJJ. So W11 is something like D1 0 0 D1, W22 is D2 0 0 D2, and E12 this will be S1 V1. This is a coupling portion. So this D1 are the symplectic eigenvalues. That means eigenvalue of J times this matrix. For instance, the symplectic eigenvalue of V11 is eigenvalue of J V11. So that's it. So the covariance matrix into written in the normal form like this. This is square root of delta 1 0 0 square root of delta 1 square root of delta 2 0 0 square root of delta 2 and diagonal of kappa 1 kappa 2, where kappa 1 kappa 2 can be determined from the known elements. This is the product of kappa 1 kappa 2 is the determinant of V12, and this equation, the total determinant of the covariance matrix is square root of delta 1 delta 2 minus kappa 1 square square root of delta 1 delta 2 minus kappa 2 square. So from these two equations one can obtain kappa 1 kappa 2 separately. So V can always be transformed into this normal form. And if we use this form 13 in the said Robertson-Schrödinger uncertainty principle, which I stated previously, that is V plus I by 2 J with the positive definite matrix, this statement is equivalent to equation 14, which reads delta 1 delta 2 plus h cross square by 4 minus delta 1 2 whole square minus tau v greater than equal to h cross square by 4 delta 1 plus delta 2, where delta 1 is determinant of V11, delta 2 determinant of V22, delta 1 2 determinant of V12, and tau v is trace of this complicated operator which I have shown. So this is the uncertainty principle. And please note that under partial transposition, the Wigner distribution, the P2 of the Wigner distribution changes flip sign. So the expectation value which lies on the V12 elements, they will flip sign. So delta 1 to flip sign. Whereas delta 1, delta 2 and tau v, that remains invariant because delta 1 is corresponding to party 1 which is unchanged, and delta 2 in delta 2 there are the expectation value of p2 square, x1 square, something like this. Although p2 changes sign, but p2 square will not change sign, so delta 2 will remain invariant. But in delta 1 2 there will be expectation value of x1 p2 something like this, p1 p2 something like this. So this p2 will change sign, so delta 1 2 flip sign. So the requirement that covariance matrix for separable state, that is the positive definite to preserve the positive definiteness after partial transposition. So delta 1, since delta 1 2 flips the sign, so mod of delta 1 2 will be replaced in the uncertainty principle. So this is this quantity which I denoted by PS, that should be greater than equal to 0 for bipartite Gaussian state, and this is a sufficient condition. If if a bipartite Gaussian state satisfies this condition, this is separable, because separable state should be transformed into a bona fide density matrix. This is positive definite matrix. So this equation 15 is a sufficient condition for which will be satisfied for all bipartite Gaussian state. If this is satisfied, then the state is separable. If this is violated, this is PS less than equal to 0, then the state is entangled. So if we have a bipartite Gaussian system, we can easily check the equation 15 and conclude whether the system is entangled or separable. So Now our main part, the non-commutative space. So in non-commutative space, we take the commutation relation between the coordinates like this. Here our the tilde correspond to coordinate in non-commutative space. So for instance, x1 tilde is coordinate corresponding to non-commutative coordinate corresponding to party 1, x2 momentum corresponding to party 1, x3 this is x2, this is coordinate corresponding to party 2, and x4 momentum corresponding to party 2, party B, Bopp. So this commutation relation is can be expressed in the deformed symplectic matrix. Please remember that, recall that the for commutative space, this was IH cross J alpha beta, where J was usual symplectic matrix, but here the deformation parameter it is deformed. This is deformed by H cross E. So H cross E is 1 plus theta eta by 4 H cross square, and in J alpha beta there is J2. This is J2 is usual J2, and pi theta eta H cross E is diagonal of theta 0 0 eta pi theta eta. So we take specifically if we write explicitly, x1 x2 is I
Hello,
theta.
can you hear me? Can I ask
Yes,
something?
yes.
Can you give me some motivation behind why you are modifying your Planck constant with this deformation parameter? I mean, what happens if you keep your for the standard Planck constant for the Heisenberg commutation bracket? I see
Okay,
that modify your Planck constant, right, with this deformation theta and eta.
yes. Uh,
Okay.
no, this we just change the fundamental commutation relation. This is x1 x2 is I theta, p1
Hmm.
p2 is I eta,
Hmm.
and x1 p1 is usual I h cross. So
Yes.
if we express if we write it in this concise form,
Hmm.
this Planck constant comes in this deformation form.
Sorry,
For
I can't
instance,
follow. No, sorry, let me understand. Your phase space algebra, where position per part is non-commutative, where theta is
yes,
the position deformation,
yes,
eta is the momentum deformation.
moment,
So
yes.
the phase space deformation. What is the commutation of x and p? It is IH bar or IH bar E effective.
I H cross. This
So
is I
what
H.
is the purpose of IH bar E effective Planck constant? What is the expression? I mean, what is the purpose of using this effective Planck constant?
Here,
As I have seen that you if you express explicitly uh, position and momentum, suppose alpha is 1 and beta is 1, so if you consider this, no, alpha is 1, beta is 2, so x1 p2, it will be what, IH bar or IH effective?
no, it will be I H cross.
Then I don't understand what is the purpose of using this modified notation. Why you are not writing this IH bar only? What is why you are introducing effective Planck constant? Is it necessary or I don't understand actually.
No, this is not necessary. For my purpose, this is right in symmetric notation. That's it. But the
But no, the
the,
symmetric
the
notation
deeper the
be
deeper meaning of the effective Planck constant, actually I don't know whether it has any deeper meaning. So no. So if
and what is the motivation behind to introducing momentum non-commutativity?
no, my motivation was to study the system as general as it could be. So that's
No, you are
it.
saying that it is a non-commutative space. So just your space is non-commutative, but you are
Yes.
considering your momentum
Also
space.
momentum non-commutativity. Yes.
So whether the entire algebra, I mean the position algebra, momentum algebra, and phase space algebra satisfy the closed Jacobi identity with this deformation?
Yes,
Because
they will.
when you have the
Yeah, yeah,
algebra, algebraic
yeah,
to
yeah,
satisfy associativity. So whether
yeah,
this
yeah, 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 yeah,
associativity,
yeah.
I mean,
Yes, yes,
whether
yes.
whether this required this momentum non-commutativity or not.
No, momentum equality is not required because we discussed that for toy model where we only consider the position non-commutativity.
Mhm.
Toy models.
And then,
So
what is the
here,
what is the physical situation? Why we are incorporating momentum non-commutativity in by hand? I mean, what is the motivation to introduce momentum non-commutativity as well as position non-commutativity? If I understand the position non-commutativity is required to understand the system in a very short length scale near to the
yes.
Planck's, then why we need requirement of the momentum non-commutativity as well? Is it necessary or it is just a
No,
wishful
it's
thing?
no, it's not necessary.
Okay, okay, understand. Okay, fine.
Okay, I just want to ask you another question. This
Yes.
J tilde matrix that you have introduced, it seems to have some diagonal element, J2.
Yes.
So X1,
No, 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 no.
okay,
J2 is 0, 1, minus 1, 0. J2 is the symplectic
okay,
matrix. So this is
Standard
0, 1.
symplectic matrix, right?
Yeah, 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 yeah.
Okay.
okay. So then in your case, what will be X1 commutator? It will be 0, I suppose.
0, yes.
Okay. And what about this? Okay, pi theta n is the again diagonal theta n, theta. But still not clear what is the necessity for introducing this deformed h bar e. Means can't you do it by simply retaining h bar, or it is forced on you to?
No, we can write in form simply H cross.
Means you could have absorbed this factor of which is occurring within the parenthesis 1 plus theta eta by 4 h bar square in one of the axes of
So,
p.
so it occurs frequently. So that's why we absorb in write by like H cross E.
Okay.
Okay, you can move ahead.
Okay. So the connection between the commutative space and the non-commutative space can be written through this Bopp sheet. This is the epsilon d is I2 minus 1 by 2 h cos pi theta eta j2 and 1 by 2 h cos pi theta eta j2 I2. This is the standard Bopp sheet, this which connects usual commutative space to non-commutative space, and with this transformation we will transform our non-commutative system to commutative system. And since the mathematical tools and the computational mechanism and all the theorem are available for commutative space, we can proceed our computation in commutative space after performing the transformation through this Bopp sheet, through this equation
But
18.
I have another comment on in this regards.
Yes,
You are
yes, yes.
saying that you can connect your non-commutative, so you can map your non-commutative phase space to a
But
standard
this, but it's
commutative.
not. But this is not unitary transformation. So
Of course, it's not. Then how could you say that the known result in the commutative space can be mapped to physically to the non-commutative space? So suppose if you can perform if you want to study a situation in non-commutative space, it
yes,
could not be the same situation for the same system dealing in the commutative space because it is not connected unitary transformation.
yes, yes,
Then how can I say that if you start looking the commutative counterpart of this non-commutative space and doing everything in a non-commutative variable, and how can I extract the result in the original non-commutative space? It is same. You are saying that if you start the mapping, if you study the mapping And if you convert your problem in terms of the commutative phase space variable, you can study usually. And then you can calculate some physical observable, so physical object. Then how can I claim that this physical object will be the same, will give rise to the same result if we start without introducing any non-canonical transformation, whether two aspects are
Well,
same.
although the transformation is not
So the
symplectic,
non-canonical transformation does not preserve the physical
however,
situation.
this epsilon d is invertible. So
Yes.
because if we calculate the determinant of this, one can see that for values of theta eta, it is invertible. So
No, and
after
I understand it is invertible, but it does
so
not mean that the two
So after
situation.
obtaining results in the commutative space,
Mhm.
uh, one can uh, so so since this is invertible, so the mapping is 1 to 1, right?
Yes.
Yeah, but it is 1 to 1. But the thing is that if you
So,
decide
so for a particular non-commutative system, there exists a particular system in commutative space.
Sorry, I could not follow your statement clearly. Are there any
that,
comments from Professor Chakraborty?
so I'm saying that if your x tilde is physical, then x is not physical. Or else you have to decide x to be physical and the x tilde is not physical. You have to decide one of the either. Since you are dealing with
Yes,
non-commutative spaces, you have to claim in the first place, you have to take the stand that your x tildes are the physical position of variables
yes,
and
yes,
x is just mathematically constructed
yes.
unphysical variables.
Yes, thank you, sir. Yes,
There's no physical relevance whatsoever.
yes,
Okay. So
yes,
now if you do further calculation, write down some so-called equivalent system or Lagrangian subsequently, I don't know what is in store ahead in your slides,
yes,
that will be scrutinized, should be scrutinized thoroughly, because you are dealing with some mathematically constructed unphysical position like variables.
yes, yes.
Okay,
Thank you.
okay,
Thank you,
please
sir.
go
Yes.
ahead.
Okay.
So, if we study the connection between the deformed symplectic matrix and our usual symplectic matrix, one can show that they are connected through H cross EJ tilde equal to H cross epsilon DJ epsilon D tilde. So J tilde is also connected through J with the Bopp shift, and the connection between the covariance matrices in the with non-commutative space is given in equation 19. This is the covariance matrix in non-commutative space connected through the covariance matrix in commutative spaces epsilon d gamma epsilon d transpose, and the non-commutative space Robertson-Schrodinger uncertainty principle reads, that is the covariance matrix plus psi by 2 h cross ej tilde. This should be a positive definite matrix. This is the deformed Schrodinger uncertainty, Robertson-Schrodinger uncertainty principle. And if we use all the
Excuse,
formula,
can I interrupt once more? Please go
yes,
back one slide.
yes, here,
This this equation, this non-commutative Robertson-Schrodinger uncertainty principle that you have written, it,
yes,
it looks very similar to the commutative version.
yes.
So are you taking this to be the given a priori or you are deriving from the first principle?
Past principle, yes.
How do you arrive at this kind of form? Because I thought that it will undergo substantial non-commutative deformation and the structure will look quite dissimilar to what it looks in the commutative case. I somehow
I think this gamma should taken care of this deformation, right, Professor Patra? What is your
Yes.
gamma D? Gamma D. What is the explicit structure of gamma D?
This
Oh,
equation A.
okay. Okay, so I think this gamma D taken care of this deformation. You see, Professor Chakraborty.
Okay.
So it will encode the information of this deformation parameters theta and eta.
Okay.
I
Okay,
think
go ahead.
okay. I understand.
So if we use the explicit forms, one can see that the connection between the blocks of the commutative space covariance matrix blocks to the non-commutative space covariance matrix blocks, where delta C epsilon is the determinant of this matrix of the Bopp shift matrix. So this is non-zero. So this is the connection between the commutative space and non-commutative space covariance matrix blocks. So these are 2 cross 2 matrices, VII, VIJ. So for an illustrative example, let us consider a non-commutative oscillator, an isotropic oscillator, anisotropy in the momentum part, the mass part, and the frequency part. And this is some linear perturbative term. So, and for our computation, we had considered these parameters as well, time dependence, time dependency of these parameters. So this is an arbitrary system, arbitrary anisotropic oscillator. And so we have calculated for both position, momentum, and non-commutative, but for illustration, for today's illustration, I have only considered the position, non-commutativity, x1 tilde x2 tilde I theta. And
Professor Patra, I have another concern. Can I ask something?
yes, sure.
I can't understand properly which parameters are time dependent for your system Hamiltonian.
The system we had studied, both m, omega, and epsilon, everything has
Okay.
time dependence. And the system was solved through the well-known Louis Rosenfeld invariant method. Through the invariant
Okay.
method.
So the point is that if I try to focus on equation 25, your
Yes.
non-commutative parameter is time dependent. Is it? Am I correct?
Will it not
Yes.
jeopardize your Jacobi identity if you have time-dependent theta?
How?
No, I don't know. Miss, have you checked it?
No.
Because if you have time dependence or theta is a variable.
Actually, I haven't checked it. Actually, this question didn't came to my mind. Whether the Jacobian will be satisfied. There is. I haven't.
Yes, it should be associative
Yes.
algebra, so it should
Yes,
satisfy
yes.
Jacobi identity. But the
Yeah, I know it should be satisfied, but that didn't strike my mind that whether that should be checked or not. Yes, that's a very
But
good.
I can't understand why non-commutative parameter theta is time dependent. It should be fundamental scale. And why this scale will change with respect to time? Then what is the meaning of fundamental scale?
No,
If
no.
we, sorry, if I am, please clarify me whether I'm going to in the wrong directions.
No, it's not a wrong direction. But actually, the system of non-commutative space and in commutative space, the particle in magnetic field, they're
Mm-hmm.
mathematically identical. So, and this theta is related to the strength of the magnetic field. So, if we can generalize the mathematical structure, study the most general mathematical model, then we can also incorporate these results for the magnetic field systems. For example,
But when we study the magnetic field Landau problem, you always consider, if I am thinking correctly, we always consider time-independent homogeneous magnetic field. But
Not
that is why
all.
you have the fundamental length scale, which is called magnetic length scale.
Yes.
But I don't understand why this length scale, if time dependent, if it is time dependent, then why it is known as fundamental scale? Because then it will change with respect to time. I mean, what is the basic motivation to introduce time dependent deformation parameter?
See, my motivation was to mainly was mathematical. I didn't thought is yeah. The question is very much important, and I will think about that. But I didn't think about that in this direction. So thank you for pointing.
So therefore, your non-commutative structure, your Heisenberg algebra, if you consider your Heisenberg algebra is itself time dependent, then how you introduce your representation space? What will be
Yeah,
the
yeah,
representation
yeah,
space of?
I understand. It will create lots of problem. For instance, we cannot.
Yes, because as I understand, the Heisenberg algebra is a kinematical algebra.
Yes,
Then you need to define your dynamics by introducing the system Hamiltonian. And
yes.
the moment you introduce the system Hamiltonian, then you can introduce the notion of time evolution.
So the Hilbert space for one particular time may not be equivalent to Hilbert space for later time. So it will
Right,
create
right.
it will
No,
create
it is
lots of
obvious. It is obvious
yeah,
because
yeah,
in a Schrödinger quantum mechanics, the Hilbert space can evolve with respect to time. The moment you can introduce the system Hamiltonian through the
yes,
Schrödinger equation.
yes.
But
But
here, you before introducing Hamiltonian, you
yes,
introduce
yes.
your
Itself,
time-dependent non-commutative.
defining the Hilbert space will be a problem. Yeah, I
Hmm.
understand. So yeah, that's a very good concern. Yeah, we'll study it further later. So thank you pointing
Okay,
out this
okay,
point.
fine. Okay.
So for illustration purpose, I just show the results. If we had considered most general case, but if we illustrate it for isotropic case, we if we compute the delta 1, delta 2, the determinant of v1, 1, v1 to tau v, etc. We can consider calculate it in straightforward manner after solving the system through Lewis-Rosenfeld invariant method. And since delta 1 2 flips the sign, the explicit expression is crucial, and which is written in 27 for this particular theta. And if we plot the delta 1 2 for isotropic oscillator with respect to theta, we can see that this is always positive. So delta 1 2 mod of delta 1 2 can be considered as delta 1 2 for all possible 0 less than equal to theta less than equal to 1. And if we consider this the Simon condition, there is the Peres-Horodecki separability criteria, we see that the PS varies like this. For theta, for this region, for first region, this is theta PS positive, and for this region, theta is negative. So for this particular value of theta, this is entangled, this corresponds to entangled state, and for particular theta from 0 to less than slightly greater than 0.4, this is separable, and for large values of theta this is entangled. So now we know that for entangled state we can extract quantum work from entangled system. Suppose two party shares some bipartite state whose covariance matrix is VC, which we have shown, and suppose B performs a pure Gaussian measurements whose covariance matrix is in terms of the rotational matrix. This is a rotation matrix, standard rotation matrix, and the conditional state of first mode A on the measurement is sigma A pi B. As a result of measurement, the reduced state of mode A, Alice, is now out of equilibrium, and Alice can extract work from a heat bath by letting her state diffuse quasi-statically in the phase space. And if we calculate if we consider the Rinai entropy, one can show that the extractable work will proportional to the logarithm of determinant of sigma A by determinant of the reduced density matrix of A. So for our system, if we explicitly the anisotropic oscillator, which I have shown, if we explicitly write down the covariance matrix, it reads like this. This is in terms of the parameters. This is mass parameters mu1, mu2, and the oscillators and frequencies. We can express all these parameters with respect to the known parameters, and this covariance matrix can be cast into this form through Williamson's theorem, where sigma A is diagonal of square root of delta 1, and sigma B is diagonal of this, and CAB is diagonal C1, C2, where C1, C2 can be evaluated from these two equations 39. This is we know delta 1, 2 we know, delta VC we know, and from this we can calculate C1, C2. So for our present case, if we calculate the delta 1, delta 2, and delta 1, 2 comes out this, and C1, C2 comes out this, equation 40 and 41. This is and this Q1, Qij's are given in terms of mass frequencies, the etc. known parameters. And if we evaluate the reduced density matrix, it comes like this, equation 45. So all in terms of the known parameters. And if we calculate the determinants of the reduced density matrix, it comes like this, delta 1, 1 minus something. So all are known parameters. So extractable work is minus KBT log of this. So since these things is positive, so the logarithm under logarithms is negative less than one quantity. So overall work is positive. So for heterodyne measurement, if lambda equal to 1, so in that case, the extractable work explicitly reads in terms of known parameters like this. And if we study the variance with respect to theta of the extractable work, we can see that for particular values of theta, the extractable work is not positive, and after some value the extractable work is positive. So for separable state, we cannot extract work. For entangled state, we can extract work. Entanglement occurs after particular values of theta. So we can show that. So we can introduce a protocol through extractable work under which we can determine whether the states are entangled or not. If the extractable work is non-zero, this is positive, then we can say that the system is entangled, and if the extractable work is not there is no extractable work, then the state is separable. So it gives experimental hand-on protocol for extracting work. So in conclusion, we see that the separability condition may be tuned in presence of time-dependent parameters. And since NC space oscillator and charged particles inside a magnetic field are mathematically same, one can exploit the present result for system under magnetic field. For instance, the measurement of weak magnetic field. And what is surprising is that generally for non-commutative space, for time-independent system, only an isotropic oscillator exhibit entangled state. For isotropic oscillator, the states are separable. But for time-dependent system, we show that even for isotropic oscillator, it can exhibit entangled state. And for interested audience, one can consult this article, to separate non-commutative space. Thank you for your patience. So I must thank the audience, especially for their valuable questions, because the few questions I didn't think in the direction, particularly for deformation after deformation of the algebra, whether it will preserve the fundamental requirement of Jacobi identity. This is a fundamental question. Thank you for that. And especially, I know, I do not know who have pointed out this, that the connection between the commutative space and non-commutative space, that was very nice knowledge for me, this valuable knowledge for me. That is actually, we are considering the non-commutative space, fundamental space has been deformed. So non-commutative space is fundamental and correct in our description. So the commutative space is just mathematical tool for our purpose. So I am really grateful for pointing out this issue to me. So I do not know who had pointed out this, but I'm grateful to him. Thank you. Thank you for your patience.
Thank you, Professor Patra. These are really nice presentations. So, is it the time for questions? Any other questions from the audience? Any other concerns about these presentations? Please unmute yourself and you can ask the questions. If you have no questions, can I ask some questions to Professor Patra?
Yes, sure.
Can you go back your slide in the conclusion section? Yes. You have mentioned that, yes, the third point, you have mentioned that the isotropic time dependent, the isotropic time independent data in
Yes.
non-commutative space do not exhibit entanglement. Is it the correct statement?
Yes, for isotropic case, for spatial
You have
spatial.
mentioned that the time
Yes,
independent system only anisotropic oscillator exhibit entangled state.
yes, yes. That's this
What
correct state.
what happened if you consider time independent isotropic oscillator in non-commutative space?
The state will be the oscillator state will be separable.
But I could not understand because the
For
moment you
isotropic case, the delta 1 2, the term V12, uh, eh, there will be no contribution from this term.
no, I
For
understand. If you go back your slide for when you introduce your system Hamiltonian, can you go back, please?
yes,
Yes, yes. If I understand correctly, in equation 24, the moment you introduce your potential, oscillator potential, whether it could be anisotropic or isotropic, the potential is position dependent, and if you introduce the position coordinate itself do not commute each other, then it really indicates, it is an indication that you can't measure two coordinate modes independently, right? If you measure one of the modes of the oscillator, then
for
other modes
isotropic,
will be disturbed,
yes,
irrespective of the notion of isotropic and anisotropic nature of frequency.
yes,
So the non-commutative algebra itself indicate that if you measure one of the modes of the system, then other modes will be disturbed due to the
yes, yes,
non-commutative deformation.
yes,
Then why you cannot expect that this will introduce some entanglement? You can't probe two modes independently in presence of non-commutativity. Intuitively, it is a well understood that if you try to probe one of the mode of the oscillator, then other mode will suffer some fluctuation due to the non-commutative space.
yes. But for
But
isotropic case,
no,
what
I am
happens?
saying that it is an independent notion of isotropic and anisotropic. The moment you have the potential,
Yes,
it is a
yes,
general consequence. It could be general consequence. Why it
yes,
is not your case? It is a general consequence. Why we need anisotropic to show up the entanglement phenomena?
yes. why this happens, I cannot tell. But what happened is that mathematically, for isotropic oscillator, if we write down in commutative space coordinate, the some angular momentum term appears. So rotational symmetry appears. Some p1 square plus p1 square plus x1 square p2 square plus some x2 p1 minus x1 p2 something term, the angular momentum term will appear, and this will commute with the Hamiltonian. So the coupling portion for which the one coordinate affects another, that probably destroyed and shows separable state.
But
For us,
when you rewrite your system Hamiltonian in terms of the commutative equivalent, I mean the commutative counterparts of the phase space variable, this system Hamiltonian boils down to some additional non-commutative correction in terms of
yes,
angular momentum, right?
yes, yes,
So this angular momentum, it should be depends on the third component of the orbital angular momentum, LZ, and which clearly indicate that it is clearly indicate the non-commutative deformation provide a coupling between x1 and x2 through this deformation. Do you follow?
but yes, I follow this intuitively because
Then the Hamiltonian explicitly exhibit the in coupling between two modes. Then why we can't expect the entropy or sorry entanglement cannot appear here? Because if we have two systems which interact through some interaction, then they should exhibit some entanglement or entanglement feature, right?
this dependency between x1 x2 somehow cancelled out due to this angular momentum operator, which exhibits the rotational symmetry of the system. And for anisotropic oscillator, this angular momentum operator becomes deformed angular momentum, which do not commute with the Hamiltonian, and then probably this is the reason for this.
Can I make some comment in the
Yes,
context?
sir. Yes, sir. Please.
Means, you see, in the non-commutative case, when you have this x1 commutator x2 is not vanishing, immediately you end up with some sort of non-trivial coupling between x1 and x2 modes. In fact,
Yes.
the well-known UVI and mixing in non-commutative field theory
Right.
is actually can be traced to this fact that in one hand, if you carry out measurement at very high energies, where you will see that ultraviolet divergences appear, it will show up as infrared divergence in the other mode. Because of the very nature, delta x, delta y, say, is greater than or equal to theta by 2.
Yes.
So who is one, the other will go up. It can be traced to that. So irrespective of whether you are considering isotropic or anisotropic oscillator, whatever it is, this is a very kinematical fact. You cannot avoid it by any kind of dynamical things. So if you want to measure one, the other cannot remain isolated, independent of that. Okay. So I think this thing should be understood in a much deeper level, what is happening here.
Yes.
Yes, because it is a kinematical fact, not it should not depend on the dynamical
Yes.
nature of system.
Yes. Because delta x1, delta x2 should be greater than equal to theta by 2. So
Yes.
some disturbance.
In fact, you can think that this is the one of the motivation to introduce the dynamical nature of space itself. You can see the when you probe one of the coordinate, then other mode will be disturbed. In fact, there are no system Hamiltonian. It is at a kinematical level. You can't measure two modes simultaneously due to the non-commutative nature.
Yes.
Then this indicate that these two modes somehow interact to each other, and which indirectly indicate that your space is now suffer by some quantum fluctuations.
Yes.
And this quantum fluctuation should be incorporated and should not be avoided for any choice of system Hamiltonian. It should be manifested in some other way.
Thank you for pointing out this issue.
Can I ask a question, if I am
Yes, please.
allowed? Like,
Yes, please.
I don't understand the part where Dr. Nondi said that the non-commutativity is related to entanglement thing. Like he explained something, but why is this something like this?
No, in fact, you can see that when you have two components of the coordinate are non-commutative, that indicate that you can't measure two modes simultaneously, right? You have some uncertainty between the coordinate sectors. So how can you say that if you try to probe, if you have a two-dimensional oscillator, and if you try to probe one of the modes of the oscillator, then other mode immediately disrupt due to the non-commutative origin of this non-commutativity, right? Do you follow?
Yes, sir.
And the point is you can't measure simultaneously two modes. And the entanglement means you can't measure two systems. Suppose if you have the total system, which is just a bipartite system, and if you have two subsystems are now interact to each other with some interaction due to the environment, it could be the effect of environment. Okay. Suppose you have a system and environment always try to interact with the system. Then how can I say that the system and environment are separated completely? If you have a closed system which do not allow to interact with environment, then you can say. So you can visualize the non-commutative space provide a natural choice of environment. You follow?
Yes. Thank you.
Okay, any other questions? Okay, if you have no more question, then we can thank the speaker again. Thank you.
Thank you.
Thank you, Professor Patra.
Thank you. Thank you for the valuable comments and suggestions. Especially.
Okay. Thanks again for Professor Chakraborty, who actually providing us important remark on this talk. Professor Chakraborty, can you hear me? I think there
Yeah,
is no. Okay, fine. Okay, so I think we can stop here for today.
Okay. Thank you. So you can leave, right?
Okay.